Good morning. So I want to make a few things or announce a few things and then move on. Mainly to prepare for exam 3, I want you to look at this solved example file. Have you looked at these module 6 and then for module 7? Not only they have solved examples, but if you look at the first, 1 second, I need to screen share so that this gets recorded. So if you go through the slides here, not only we have done examples, but the slides were also created during lecture. This was back in fall 2020 during the COVID time. So I used to lecture by typing these out like I do in class, just like writing, I used to type these out. So you should review these summaries of pipe flow and losses and stuff. That will actually kind of be a refresher of what we learned in class. So general characteristics of pipe flows, what is laminar versus what is turbulent, and then features of turbulent flow, what is entrance length. We talked about this in our class also. Why we need a pump to make a fluid move, because there is energy loss and the pump has to make up for that. And then the losses in the entrance region versus the fully developed region, how it becomes non-linear in the entrance region and becomes linear later. And then we talk about the entrance length calculation. As you will see in your mock exam, this formula is needed for solving a problem. We'll go through that. And then after that, it talks a lot about how to use this equation, which connects flow rate through a fully developed pipe flow with the pressure drop and the diameter and the viscosity and length of the pipe. Dimensional analysis of pipe flow, and then we start with example problems. So we are going to go through some of these, but I strongly suggest that you work out all these problems by yourself and check against the solution. That would be good preparation. It would cover all the topics that you're supposed to know once you clear this class. Okay. If you skip this, I can't guarantee that you will do well in exam 3. I'm putting it bluntly. I was just printing exam 3. I know what's on there. If you skip this, you're not going to do well. Take it from me. And whether you feel that exam is easy or difficult, there is not going to be makeup. There is not going to be any more chances. This is it. Exam 3, you do it on Tuesday, and that's pretty much the end of the line. Okay. So please prepare well. If you're not afraid, if you're not scared, what can I tell you to scare you? Okay. So each problem I also try to put some discussion about what went on, and I wish I could find these lectures when we did this, because this was done in live during class. So unfortunately, I could not find those class recordings. So do these, okay? And if you have questions, email me, come see me, we'll talk. Hopefully by the time you show up for exam on Tuesday, you have a better grip on this topic. Okay. And today, if I can, I'll do some more examples. And then module 6 is not that complicated. It's scaling analysis. One thing that came out of the project, all of you did scaling analysis reasonably well. I was actually impressed. I told the project scores were between 17 and 19 out of 20. They were all reasonable. That's there. But most of you, or actually none of you, paid attention to resolution error or the uncertainty in your measurements. You all did some markings or calibration that was kind of loose, and it was not well thought out. And the numbers that you put out as flow rate or time, I don't know whether the error on that is 10% or 1% or 50%. That was not clear, but you can see the score is 17 to 20, meaning 85 to 95. So I've basically given 85% minimum, 95% maximum to reward your effort, but it could have been just a little bit better in my view. Okay. But for a first time, I thought that this project experiment succeeded. So please do these problems for again for scaling analysis. There is a lot of also explanations why we do things the way we do. So please read through those. Okay. Any questions regarding how to prepare for exam 3?
The formula sheet policy is still the same.
Yeah, you can bring 2 sheets. That's still fine. Okay, and I'll provide the Moody chart and the tables to look up the loss coefficient. Okay. Um, all right, good. So then, in front of you, we have you should have this mock exam that I printed out a copy. So please share it in. One of you need to switch seats. Okay. So let's quickly go through that and discuss those. So take a moment, read the first problem, and we'll start. And I'm hoping after this, I can also do one or two problems on module 7. Please read the problem. I'm not going to read it. So we are told a cone and plate viscometer as shown consists of a cone with a very small angle alpha that rotates above a flat surface. The torque required to rotate the cone at an angular velocity omega is a function of the radius r, the cone angle, and the fluid viscosity in addition to omega. So the torque is a function of omega, the rotation velocity or angular velocity, radius of the cone, and the angle alpha, and this fluid viscosity mu. With the aid of dimensional analysis, determine how the torque will change if both viscosity and angular velocity are doubled. Okay. Now, what do you think is the purpose of a cone and plate viscometer? How do you think this device will be used in practice? So we have this cone. Here's the vessel. The fluid is filled in here, and then there is a rod which is made to rotate at a certain angular speed. What do you think is the purpose of such a setup? Yes. Yeah, go first.
The torque is a function of the viscosity, but if you know what the torque is, you can just solve it with like how much torque, given all the other things it takes to move something at a certain viscosity.
Right. So by measuring, what did you want to say?
Operates the same thing.
Okay. By measuring the torque gamma required to spin the cone at a known or measured angular speed omega, the viscosity can be measured if the relation between gamma and viscosity and the other quantities, if the relationship between gamma as a function of the other quantities, which include omega, r, alpha, and mu, is known. This is the practical context for this problem. So first thing we want to do is to express this in scaling in non-dimensional form. How to do the scaling? This is your exam problem. What's your first step?
Eller.
Choose a reference length we need to choose a reference length, which obviously can be the radius because it's the only length present. What is a good choice for reference time? That would be
Omega.
omega has units of what?
Radians per second.
Radians per second, right? So omega has units of radians per second. So a quantity which is omega over 2 pi radians will have units of per second. So a quantity which is 2 pi over omega will have units of second. So a good choice for reference time would be 2 pi over omega, because that's the quantity that has units of time. Alpha is an angle which may be measured in radians. So we'll just leave that as it is. We don't have to non-dimensionalize it. Okay. And what's the unit for viscosity? Viscosity is Pascal times seconds. Thank you. So that is Newton per meter squared times second. That is kilogram meter per second squared times per meter squared times second. Or this is kilogram per meter per second. Or the dimensions would be m, l, t to the minus 1. So one of them is your reference length. The other gives you a reference time, and mass is contained only in viscosity. So this can yield you a reference mass. How can it yield you a reference mass? M reference would be, or if I say viscosity divided by M reference times L reference to the power minus 1 and T reference to the power minus 1, this quantity has to be unitless. This quantity has to be unitless. So I can write viscosity divided by M reference. What is my reference length? R to the minus 1, and T reference is 2 pi over omega to the minus 1. This quantity has to be unitless, which means mu R 2 pi over omega divided by reference mass has to be unitless, which means a good choice for reference mass would be mu R for 2 pi over omega times mu R. So you have all these three quantities already used. So how many dimensionless numbers are we going to get remaining? How many are we going to get? We are leaving this alone. How many are left behind now? How many groups are we going to get? So you just have torque left. Let's non-dimensionalize the torque. So torque, what are the units or dimensions of torque? Newton meters, right? So that's kilogram meter per second squared times meter, which is kilogram meter squared per second squared, or m l squared t to the minus 2. Once you write it like this, define a quantity called pi, which is gamma divided by m reference, l reference, t reference squared minus 2. So this is gamma divided by What is my reference mass? 2 pi omega mu r. L reference is r squared. T reference is 2 pi over omega to the minus 2. This is gamma times 2 pi over omega squared divided by 2 pi over omega mu r cube. So this is 2 pi over omega times gamma divided by mu r cube. This is pi. Pi equals 2 pi over omega times gamma divided by mu r squared. If one more person comes along, share it.
Why is it R squared if you're you?
Have you copying it? If two experiments are done, two measurements are done that have the same non-dimensional torque, which we have given the symbol pi. We have pi 1 equal to pi 2, 2 pi over omega 1 times gamma 1 over mu r1 cube or mu 1 r1 cube, 2 pi omega 2 times gamma 2 mu 2 r2 cube.
Wait, so is pi a variable here?
Pi is not a variable. Think of it as you are designing you and I are doing two experiments. You are working with SAE oil 40. I'm working with SAE 20, let's say. They have slightly different values of viscosity. So you choose different rotation speed and measure a slightly different torque. I choose a different rotation speed and measure a slightly different torque. But we ensure that globally this ratio remains the same.
So pi is the ratio.
Pi is the ratio, pi is the non-dimensional torque. Okay. So the question is, what will happen to the torque if both the viscosity and angular velocity are doubled? What will happen to torque? So if I say gamma, if 2 pi over omega times gamma over mu r squared is a constant. If I replace omega with 2 omega and mu dash with 2 mu, what should be the new value of torque? That would be, or I will write omega 2. Omega 2 is 2 omega 1 and mu 2 is 2 mu 1. What will be gamma 2? So that would be, assuming radius is the same. If it's not told, we'll assume radius is the same. Gamma 2 will be gamma 1 times 2 omega 1 times 2 mu 1 divided by omega 1 times mu 1. So look at this, and I'm saying it will be 4 times the torque. Look at this step and tell me if it makes sense. because I skipped 2 steps in between intentionally. The last lecture, so I don't want to make it too detailed. Look at this step and tell me if this makes sense to you. If it doesn't, I'm happy to explain. Okay, Raj? This common factor 2 pi goes out. We assume radius is remaining same. And we are just wherever 2 appears, we are substituting as 2 mu 1. And wherever omega 2 appears, we are substituting as 2 omega 1. That's what these two are. And then we are getting 4 times gamma 1.
Could you also take I set it equal to f is alpha, and just divide it over, like isolate the torque?
That is, you're saying gamma, that is 2 pi over omega divided by mu r squared equal to a function of alpha. And for a given design of the viscometer, this is a fixed value. So if you did 2 experiments, obviously pi 1 and pi 2 has to match. That's another way of, that's a good way of saying.
Right, but another way you could solve this is just isolate gamma by dividing all the terms around gamma over the other side and multiplying mu and.
You can, and that's what this is. These two are exactly the same thing mathematically. Is everybody good? I'll be able to see why this torque will be 4 times if you double both velocity and radius. Sorry, velocity and viscosity. Okay. Same question. If I ask you, what will be the torque if only the radius is doubled, but not the other two? What will be your quick answer? If R2 equal to 2R1, keeping others fixed, what will be gamma 2? Quick, 30 seconds. 8. Not 1/8, 8 times. That is, if R2 is 8 times R1 cube, then gamma 2 will be 8 times gamma 1. Okay? So you have to see these proportionalities. It depends on omega to the power 1, mu to the power 1, and radius to the power 3. So you double the radius, you get 8 times the torque. Okay? This kind of a question is appearing, I'm telling you. That is, once you derive the scaling relationship, or once you have a relationship, doubling something, tripling something, and understanding how that will impact the quantity being measured. Okay? Any questions? Can we move on? Okay. Please look at the next problem. Second. This was problem 1.
I have a question.
Yes.
I don't know if, oh, wait, never mind. I think you just, never mind. You substitute. Okay.
I like the way Brian put it. If you bring everything to everything that can be varied is brought to one side, and for the given device, the angle is a fixed number. Once you decide 8 degrees, it is 8 degrees. You can't keep changing the design. So if I run an experiment with oil 1 and he runs an experiment with oil 2, we both will measure slightly different torques and slightly different rotation speeds because our fluids are different. But the idea is their combination should be equal. That is what pi is, their combination, the non-dimensional torque. So this is like saying this is equal to f of alpha, which is nothing but a constant number. Okay. All right, problem 2. Student drops two spherical balls of different diameters and different densities. She has a stroboscopic photograph showing the position of each ball as a function of time. However, she wants to express the velocity of each as a function of time in dimensionless form. Develop the dimensionless group. The equation of motion for each ball is given, where m is mass, cd is drag coefficient, a is area, and v is velocity, t is time, and rho is density of air. Can I erase this? Can I erase this? So problem 2, m dv dt equal to mg minus half minus cd over 2 times rho a v squared. Okay, so she has calculated velocity as a function of time, something like in your experiment, except this is a dropping ball. And we want to plot the velocity and time in dimensionless form. So if you think of velocity as your observable, what are the quantities that influence velocity? Velocity is a function of what?
Distance.
Sorry?
Distance.
That is the definition for velocity. I'm asking from based on this relation, what all quantities will influence the solution for velocity?
Gravity, mass,
Gravity,
density,
mass, density of air, the area of the surface area of the ball, and the drag coefficient. Yes, and time. Yeah.
We have things that are constants that are never gonna change to bases.
We do because if she did experiment with two different objects and they both have different masses or different densities and size. So how much velocity you measure is going to depend on the size and mass. So they do influence the problem. That is, whether your curve looks like this or looks like this, is this is for M1 and this is for M2.
No, but I'm asking about things like the gravity and the drag coefficients, those stay the same between the two.
They stay the same between the two, but what I'm saying is they do influence the problem, so you have to include them. Like if you think of another experiment where you take a single object, do the same experiment in two geographic regions where G is significantly different, then you can say G influences the problem. G is also a parameter you're varying in your experiment, although doing that in practical terms is quite tedious. Like you have to do an experiment in Memphis, travel all the way to Norway and do the experiment there.
But if we're comparing two different experiments, like they're just gonna cancel, right? Because gravity is the same, the drag coefficient is the same, so.
They will cancel in the sense they will have the same non-dimensional value. Won't cancel. Okay. So for this problem, what are good length scales to pick? What is a good reference length scale for this problem?
area,
Sorry?
area.
Area is not a length, so how will you make it into a length? Square root of area. So you can write 4 by pi times area square. That will give you diameter, right? So that's a good reference length. CD is unitless as it is. You don't have to non-dimensionalize that anymore. It's already non-dimensional. And this quantity has already been used. This is mass of the ball, and this is density of air. So which one should be used for reference mass?
Okay.
Sorry?
And
M. So we'll use reference mass as M of the sphere.
in your L reference, why did we do the square root of 405?
That is, if they are telling us this is a sphere and it has a surface area A, okay, which has units of meter squared. So I am considering if it's a sphere A equal to pi by 4 b squared. So if I want a length, a convenient length to think about is 4a by pi to the square root.
They were solving for D.
In essence. But here's the catch. You can always have an area even for a non-spherical shape. So instead of this being a nice regular sphere, what if that shape is like a pollen or a golf ball for which the area is not exactly this? So you can always use the measured area because there are methods to measure area directly and use that area as a length scale. This is the part that you guys are kind of going to learn as you progress through your life. The choice of reference length, reference mass is usually dictated by what is most easily measurable. It's not by what's the most repeated quantity or anything here. In this list, I could say I'm going to use G, but G is not a something that I can measure. I can look up probably. The most relevant measurement would be area. Could be a golf ball, pollen, tennis ball, whatever. Area is something you can measure. Okay. All right. So then, what is a good reference time? T is the real time that you measure with a clicker. But what in this scale, what is the reference time that we can use? The only other quantity that involves time is G. So we would have L reference divided by G square root. So this is 4a by pi square root divided by G. So this is length or this is meter. This is meter per second squared. And then I have to take a square root to bring this to here. So this would be 4a by pi to the 1/4 divided by square root of G. That's not very pretty. So if the student or whoever is doing it wants to plot this in non-dimensional form, they would plot non-dimensional velocity being the real velocity divided by L reference times T reference to the -1 and time non-dimensional would be time divided by T reference. So you have already identified what is L reference, what is T reference. Question though, will this, obviously this plotting involves this length and time and only time. Does M reference have any role in this problem? Does mass have any role in this problem at all? Yes, no, first. Does mass of the object or the ball in this case have influenced the falling time or the velocity with which it falls? No. Look at this equation. Yes. So this is dv over dt equal to g minus half rho v squared times or cd times half rho v squared times a divided by m. What do you know from your dynamics or your high school understanding of particle dynamics? If you neglect drag, if there is no drag, then this equation is simply dv over dt equal to g or v of t equals initial velocity minus g plus g. Does mass influence it if there is no drag? Yes or no? No. This is the famous experiment. You can drop an object which is like a ball or which is like a plastic, different densities, but they fall exactly the same because the drag or the equation of motion doesn't depend on mass directly. But if you include air resistance, the acceleration produced by drag is inversely proportional to mass. So mass does influence this problem. So if you did experiment with two different masses, they will have different curves or different rates at which they fall. Okay, think about it. So to answer this problem, this is the plotting that she needs to do. To plot velocity in non-dimensional form as a function of non-dimensional time. Any questions before we move on? Good, okay. Problem 3. Please take a look. So first two problems will be from module 6 based on scaling analysis. That's what we just did.
So what is the answer for problem 2? Would it be the there?
Come again?
What would be the answer for problem?
This one. Either you can write this in words or you can draw a simple x and y graph and plot or write the quantity here. I mean, prior to that step, you should have identified what is LREF and TREF. So this will be the final answer that I would present.
So you don't need to plot anything.
You don't have any data. If I gave you a data of V and T, then you will plot the data in non-dimensional form.
Okay.
Okay. Problem 3, please take a read. I think we did this problem or something similar. To cool a given room, it is necessary to supply 4. So Q is 4 cubic feet per second of air. Okay, through a pipe whose diameter is 8 inches. Approximately how long is the entrance length for this pipe? Okay. If an entrance length problem appears in the exam, I'll provide the bottom equation. Because it's not reasonable for me to expect people to memorize this, which I will never do. I don't expect you to. So, but you still need to know how to go about this problem. Can somebody tell me the sequence? What's the first step I should do? We talked about this last lecture.
Probably convert.
Sure. If you're like me, you want to convert this to SI first. So this is 8 inches times 0.0254 meters per inch. You can do that conversion. And Q, 4 cubic feet per second. This is 4. 1 feet is 30.48 centimeters. Again, if there are any unit conversions, I will provide that, but my intention is to give problems in SI unit. Centimeters of 0.3048 meters per feet, okay, times cubic feet per second. You can do this. I mean, I need to cube this. Yeah, so you can do this. What's the next step after you convert units to your favorite system?
Find if it's laminar or turbulent flow.
To do that is like the third or fourth step. Before that, what do you need? To do laminar or turbulent, you need to compute what? Reynolds number. See, look at the equation below. Reynolds number is given, sorry, the correlation for different laminar flow and turbulent flow is given. It depends on Reynolds number. You need to remember two things. What constitutes laminar flow and what constitutes turbulent flow based on Reynolds number. I'm not going to give you that information. We talked about this for pipe flow. What is the cutoff criteria?
2300.
2300. So you compute Reynolds number. If that happens to be 2300, it is surely laminar flow. That's what's been experimentally observed so far. But if it is more than 2300, it is very likely to be turbulent flow unless special care is taken. That is, I'll write it here. It's a good moment to repeat this. If Reynolds number is less than 2300, the flow is strictly laminar. Do you have an extra sheet with you? Isaac,
No.
you might want to share with someone, with them. If Reynolds number is greater than 2300, unless special care is taken, the flow is probably turbulent. So to make this decision, you need the Reynolds number, and to get the Reynolds number, what do you need? What is Reynolds number? I'm not going to give you that.
It's V times velocity times diameter of viscosity.
Rho VD over mu. So essentially, the problem starts with you trying to calculate each of these quantities for the situation here. So what is density and viscosity for air? Nothing else is told, it just says air. So what's your baseline assumption to be about air? Room temperature, standard temperature and pressure. So you can assume something nominal. You can think it's like 20 degrees Celsius, 1 atmosphere. If you did 25 degrees Celsius or 30 degrees Celsius, that's also okay. There's no harm in that. Pick the temperature and pressure that's nominal and calculate density for that. Or you can do this by ideal gas equation or use data tables, which will be given to you. Look up the data table. Okay. So density of air at this condition is approximately 1.2 kg per meter cube. How I know? From memory. You are also welcome to use your memory as long as it's the correct one. And viscosity of air is about 1.8 times 10 power minus 5 Pascals. It can also come from the tables. And what is B? We know D. It's given in the problem as 8 inches. And what is B? The nominal velocity. What's a good nominal velocity here? For pipe flow, if flow rate is given, what's a good nominal velocity?
Q over A.
Average velocity, right? Q over A. So you can calculate those. So you plug in everything and then get Reynolds number and then make this decision. Okay. I did post the solution to this entire exam already. I wanted to talk about this, but I'm trusting you can do this calculation. The solution is already online, okay? So, okay, just so we actually use one of those two entrance length relationships, can we at least estimate Reynolds number? So this will be 0.3 cube, which is this is 0.027 times 4 meter cube per second. That's 0.108 meter cube per second. And this length is 0.2 meters. Okay, so Reynolds number would be 1.2 kg per meter cube times, I still have to compute velocity, which I can replace with the Q over A, Q being 0.108 meter cube per second divided by 5 by 4. I have 0.2 squared or 0.2 squared meter squared times diameter is 0.2 meters and mu being 1.8 times 10 power minus 5 pascals. Can we please compute Reynolds number? Can you tell me? 47,000. Okay, so you get a Reynolds number 47,000 and then you come to this decision making tree. What's your decision? Reynolds number being 47,000 gets us turbulent flow, which means you have to pick the second expression. Entrance length equal to 4.4 times Reynolds number to the 1/6. So that's 4.4 times LE over D. LE over D. So this is 47,000 to the 1/6. So if you want entrance length, you have to multiply this by D. Can we do the calculation? What is this number first? Can I get this first? 47,000 to the 1/6 power times 4.6.007.
Yeah, 26.
What did you give?
Yeah, 26.
Okay, we'll wait for one more answer. 26. Okay. So this is L over D is 26. So the simple interpretation of this statement is the entrance length is 26 diameters. So if your diameter is 1 inch, it's 26 inches. Our diameter happens to be 8 inches, which means LE in inches is 26 times 8 inches. But it's not the actual number that is important. The number that's important is what is the entrance length as a multiple of the reference length, which is 26 times. So it's 26 diameter. Very common practice in fluid mechanics to talk in terms of diameter. diameters. How much is the entrance length? Oh, it's about 26 diameters. Okay. You always define your local scale based on the problem involved. It could be 8 inches or 8 feet, but the fact is, it is 26 diameters. Okay.
Going 855 for interest on.
Sure, the actual number in inches is fine. Yes.
So is the answer LE or LE over G? What is that?
There is no the answer, there is only an answer. An answer is to say in inches for this problem. An answer is also to think about what is the entrance length in terms of the diameter, which is 26 diameters. I know you're asking in the context of the exam, what should I leave it with? You should leave it with. In life, where does this matter? Suppose you are laying this pipeline to carry gasoline at this rate, or in this problem, it's about airflow into a room. Okay, so if your total piping length is, let's say, 20 feet, what fraction of your entrance length is this? What fraction of the total length is entrance length here? If LE happens to be, how much did you say? 500 inch?
In inches is 208.
208 inches. If the total length of the pipe happens to be 20 feet, is it reasonable to neglect the entrance length portion in your flow rate calculation analysis or pressure drop analysis? Yes or no? Is it okay if I neglect the entrance length in the context of 20 feet of piping?
Yes.
Yes. Why? Because how much this is in feet? That is
17.
about 17 feet. Now tell me if it's okay.
Can't take it.
Can neglect if it's the context is 20 feet. But if I tell you the pipeline is about 200 feet in total length, then it's okay? Because then it comes within 10%. So it's probably okay. So entrance length by itself, only in this course, only in this exam, somebody will just ask you to calculate entrance length because they are trying to see if you understood or remember the formula. But in real practice, entrance length is usually an intermediate step calculation in a bigger picture analysis, where you are trying to see whether it's significant or insignificant compared to the total length of pipe that you are trying to analyze. Okay. All right, we have half an hour. Problem 4. A liquid with specific gravity 0.96 and viscosity given as here, that is 9.2 times 10 power minus 4 Pascal seconds, and vapor pressure of 1.2 times 10 power 4 Pascal second absolute, is drawn into a syringe. What is the maximum flow rate if cavitation is not to occur? So you have a picture there. I don't want to redraw that, but what we are saying is the flow rate through the syringe is going to be, I should write it first. If you draw liquid through a syringe, you're going to create a pressure drop. That's what will draw the liquid in, right? How do you suck liquid in using a syringe? You have to pull the plunger which creates the pressure drop, and that's what sucks the liquid into the syringe or into the needle and into the syringe. That making sense to you? You've done this many times, I'm sure, using a syringe for whatever purpose. Yes, no? Yes? So what will happen if you draw the plunger too fast, then you drop a lot of pressure. What will happen if Q is beyond a certain value? If Q is greater than some critical value, Q creates a pressure drop, creates delta P. If the delta P created is more than the vapor pressure, what will happen is the liquid will evaporate. Liquid will turn to vapor. This one is sudden adiabatic evaporation. You suddenly pull a liquid through, it will vaporize and turn into liquid. What they are asking in this problem is, what is the maximum value of flow rate that you can go such that cavitation does not occur? So there is this portion, this part is called cavitation. The pressure should not suddenly drop below the vapor pressure of the liquid. That's what is asked in the problem. So we want to calculate the Q max for which delta P is equal to delta P, that is the vapor pressure, so that we are just short of cavitation. Like calculating the maximum possible flow rate. So what you want to do is assume delta P equal to PV, which is given as 1.2 times 10 to the 4 pascals. And for this for this delta P, compute Q. For this delta P, compute Q. Okay, so Q for fully developed laminar pipe or Q. So Q is pi over 128 mu delta P over L times d to the fourth, or pi over 8 mu delta P to the L r to the fourth. This is probably something that should be on your equation sheet, because this is the only thing we discussed in class. So you should have this formula written down somewhere. Now look at the picture, please. You have the syringe and then you have the needle. Okay, the syringe is 10 mm in diameter, and the needle is a quarter mm in diameter. The length of the needle is 0.10 meters, and the plunger. The total length is 0.12, meaning to scale or not to scale. This is 0.20. Before you calculate anything, in which portion, this portion, the syringe portion of the needle portion, will the pressure drop be maximum? Where will most of the pressure drop? where will most of the pressure drop?
Needle.
In the needle. Why? Because needle is only half a quarter millimeter, whereas the syringe is 10 millimeters. If you look at this equation, for the same Q, that is, if you are pulling a liquid, the same Q goes through the needle, through the syringe, the same Q is entering here. So if you assume Q is constant, Q is pi over 128 mu delta P, okay, total, okay, delta P total. I shouldn't write that. Q is pi over 128 mu delta P1 divided by L1 times D1 to the 4. Q is also equal to pi over 128 mu delta P2 over L2 times D2 to the 4. It's the same flow. I can apply the same equation for the first section and for the second section. It's the same flow rate. I'm just applying the equation twice, one for section 1 and one for section 2.
So what what are you doing is you're getting the part from the syringe and the part from the part from the needle, the part from the syringe and adding them? So
That's the next step.
oh, okay.
So I can take this equation and write the pressure drop in the first section should be 128 mu divided by pi times QL1 divided by D1 to the 4. And from this equation, delta P2 is 128 mu divided by pi QL2 divided by D2 to the 4. So if I add delta P1 plus delta P2 is equal to delta P total, which we know is equal to the vapor pressure, and this is equal to 128 mu divided by pi times Q L1 D1 to the 4 plus L2 D2 to the 4. We have set up the equation for the total pressure drop in terms of the pressure drop in each section. Without doing any calculation, you could say the pressure drop in section 1 will be much more significant than the pressure drop in section 2, because they have a diameter ratio of nearly 10 divided by 0.25. That's 40 times. If the diameters differ by 40 times, how much will the pressure drop differ by? 40 to the 4th power. So this that is, if you see here, if diameter differs by delta P1 divided by delta P2 is like D2 over D1 to the power 4. That is 40 times 40 to the power 4, which is a huge number, or in other words, delta P1 is this factor times delta P2. So if somebody asks you as a mechanical engineer, where is most of the pressure drop in the syringe? It's almost everything is in the needle compared to what is in the syringe itself. The needle causes most of the pressure drop. A very minuscule portion is dropped in the syringe itself. Okay, we'll come to that. So now in this equation, which are the quantities we know and which are the quantities we don't know? In this equation,
Everything except Q.
we know this is given. We know L1, L2, we know D1, D2, we know the fluid, so we know viscosity. We need to solve for Q. solve for Q. So Q would be 5 over 128 mu times delta P total multiplied by L1 D1 to the fourth plus L2 D2 to the fourth inverse. Do the calculation, please. Viscosity is given, pressure drop is given, viscosity is 9.2 times 10 power minus 4. So this is 5 over 128. 9.2 times 10 power minus 4 Pascal second times L1. L1 is 0.10 divided by D1 0.25 0.25 0.1 meters. So this is 0.25 millimeters. So I have to multiply this by 10 power minus 3 before I take the fourth power, plus this is 0.02 meters divided by 10 times 10 power minus 3 to the power 4.
Where'd you get 0.02 from?
So this in the figure, the needle portion is set 0.10 and the total length is given to be 0.12. So I took the difference. Yes,
You not multiply by delta PT.
yes. So delta P would be 1.2 times 10 to the 4 pascals. You should also keep an eye on the unit. So this would be meters to the fourth power. This would be meters to the fourth power. In the end, Q should have units of meter cube per second. That's a consistency change.
That inverse the. Do we inverse that whole bracket?
Inverse the whole thing. So let's push through this. So you have 25 is 1/4. So you have what is 4 to the fourth power? 1024. Right. So 0.10 times 1024 divided by 10 power minus 12 to the fourth power, that is say meter cube, plus 0.02 times 0.02 divided by 10 power minus 3, sorry, 10 power 3 times 10 power minus 12 meter cube. Or you can punch this in your laptop and tell, yes.
Why aren't we taking the pressure difference? Because we're given the pressure in terms of absolute, not gauge. So
That is-
we subtract.
So we are given the absolute pressure 101 kPa. Okay, we'll write that here. Okay, and the vapor pressure is 12,000 Pascal. PA, PV. So if we represent this is PA and this is PD, the pressure drop cannot be more than cannot drop below P. So the allowable pressure drop would be PA minus PV. So I guess this must be the value that should have been used, not PV. Delta P should be, delta P total should be PA minus PV, which is 101,000, 101,000 Pascal minus 12,000, which is 89,000 Pascal. 89,000 Pascal. I totally missed the bottom.
But if we were given gauge pressure, we wouldn't have to do that. We could just directly substitute the given pressure.
If gauge pressure is given, then this is considered zero in gauge pressure because you will subtract PA minus PA, and then PA minus PV minus PA will be a negative number. You will invert that number. But what I missed is I just assumed this with respect to vacuum, so I just took it directly. But what I should have done, thanks for catching that. If you are at atmospheric pressure and you pull the plunger, you are dropping the pressure. You should not drop below PV. So from 101,000, don't go below 12,000. If you go below 12,000, you will start cavitating or start forming bubbles in the syringe. Okay. So the value we should use here is not 12,000, it's 89,000. It's 89,000. So as you can see here, this number is like 102, whereas this number is a very small number. It's 2 times 10 power minus 5 compared to 100. If you take this here, this is 102.4 plus 2 times 10 power minus 5 divided by 10 power minus 12, which I am supposed to invert. So compared to this number, 102.4, this is almost like a rounding error. So you can almost forget the syringe in your analysis and still get the answer correct. Right? Are you going to say something?
So we didn't actually define delta P one and delta P two.
No, I made that because I wanted to make this point. If I just asked you to don't worry about the syringe, you wouldn't know why. Now you know why you don't need to worry about the syringe. Almost all the pressure drop is in the needle and none of it or almost none of it is in the syringe. Okay. So we bring it here times 89,000 divided by 9.2 times 10 power minus 4, and I have 10 to the 12 divided by 102.4. So this is the, I'll call this 9 times 10 power 4. I'll call this 9 times 10 to the minus 4. I'll call this 100. Okay. So this is 10 power 10, 10 power 14. No. Okay, I'm sorry, I don't want to spend any more time on this. I'm not good at this. Please go home, complete it. The solution is in the solution document. Okay, so please complete this. I have 10 minutes. Last problem. Person with no experience in fluid mechanics wants to estimate the friction factor for a 1-inch diameter galvanized iron pipe at a Reynolds number of 8,000. Okay, so Reynolds number is directly given to us. It's 8,000. Problem 5. 1-inch galvanized galvanized iron pipe. Reynolds number is given as 8,000. Okay. The person stumbles across the simple equation of 64 divided by RE and uses this to calculate the friction factor. So they use this with F is equal to 64 divided by RE, which is applicable for laminar flow. So F would be 64 divided by 8,000, which is 1 over 125. How much is that? Can you tell me?
0.008.
0 points. Oh, I should have done that. Sorry. Brain freeze. 0.008. Okay. Now, based on the information that this is galvanized iron pipe and the Reynolds number is 8,000, you can also look up the friction factor as a function of Reynolds number and the roughness from the Moody chart, and you can figure out what value of F you will get when you consider that this is turbulent flow. Because it's 8,000, it's expected to be turbulent. So if it is turbulent, what will be the friction factor? So switch over to page 430, which will be provided during the exam. 431, sorry. Use that Moody chart to calculate the friction factor at Reynolds number of 8,000. And for galvanized iron, the roughness is 0.0005 inches. So epsilon is 0.005 inches. This is from table 8.1, also will be given. So for this pipe, how much is epsilon divided by D? That's 0.0005 inches divided by 1 inch, or this is 0.0005. So look up for Reynolds number equal to 8,000 and epsilon over D equal to 0.0005. If you do that, F comes out to be about 0.032. Those who have the text, can you confirm this? Okay, take a pause, look up please, an important point. The friction factor at Reynolds number 8,000, if you mistakenly think it would be laminar flow, is coming out to be 0.008. If the flow were turbulent, the friction factor comes out to be 0.032. So just consider the ratio F turbulent divided by F laminar. 0.032 divided by 0.008. That's 4 times. How do you interpret this ratio? The friction factor is four times more in turbulent flow than in laminar flow at the same Reynolds number. What is the implication?
It means like the air is forcing itself onto the wall more, causing more like that.
What happens is in turbulent flow, you have more mixing, the losses are higher. Okay. If you underestimate your losses by a factor of 4, what is the implication of that for your pressure drop calculation and eventually for your pump selection? If you mistakenly pick laminar, you are underestimating the pressure drop by a factor of 4. What is pressure drop? Pressure drop is delta P equal to F times L divided by D times what did we see last time? See, F divided by RE times L divided by D. So delta P for turbulent would be F turbulent divided by delta P for the laminar will be F laminar. keeping everything else the same, for the same pipe, for the same Reynolds number. So getting this decision right is crucial because two reasons. One is turbulent flow on an average will always have higher loss, pressure loss than laminar flow. If you mistakenly think a flow is laminar when it's turbulent, you are massively underestimating the pressure drop, which can have serious consequences on how much pressure drop you calculate and what pump you select for your particular application. So getting it right, that is getting the Reynolds number calculation right, then making a decision whether it's laminar or turbulent, then calculating the friction factor either using the laminar formula or the turbulent chart is a crucial part of estimating pressure loss. That makes sense? So this number should be something that you should remember. Turbulent flow always has more loss than laminar flow at the same Reynolds number. Almost always true. Okay. If the turbulence intensity comes down, eventually the difference will come down. But as the Reynolds number increases, this number will only get worse. Okay. All right, good. So that kind of wraps up our discussion. I want to reiterate two things. Please look at the posted solution for mock exam, practice similar problems, and to find similar problems, look at module 6 and module 7, solved examples 5. Okay. The material you need for the final has all been covered now. So you are welcome to work on the final. So from now on, we have exam 3, that's on Tuesday, 2 sheet of notes, 75 minutes in class. For final, please don't consult with anyone. Please don't use AI. I'm trusting you will not cheat. It's due by when? May 4th, midnight. No extensions. Okay. And for the last 3 points to do the course evaluations, I've given you until May 5th. So please do the course evaluations, provide feedback, and that carries 3 points. Okay. Any questions before we go? Yes.
Will we calculate losses for the exam?
Come again.
Will we need to calculate losses for the exam?
You may be asked, there will be calculation. Yes.
Okay, like minor and major losses?
Yes, absolutely. Whatever we covered so far, whatever is in the solved examples file is fair game for the exam. So you should practice all of those. Okay. This is the wrap up of the course. Been fun. Thank you so much. See you Tuesday.